Hello YouTube! My name is Dylan Rambow. I'm a PhD student at Northern Illinois University, and today I want to talk to you about number fields, and in particular how primes and absolute values work in number fields. So a lot of what I say today will piggyback off of some of the stuff I talked about in the p-adics video that I have already uploaded. So if you haven't seen that, go watch it first. The link will be in the description. So for starters, a number field is just a finite algebraic extension of the field of rational numbers. And to study how primes work in these number fields, I want to focus just on the one example of the field of Gaussian numbers. In any other number field you could ever want to study, the ideas behind it of how primes behave in those fields will be exactly the same as what we're going to study here, but just the actual computation of what are the primes in such fields, how do you find them and such, it's more complicated in other fields. That's the only difference in other number fields besides this one. So you should note that the field of Gaussian numbers is just the fraction field for the ring of Gaussian integers, much like the field of rational numbers is the fraction field of the ring of integers. So when we talk about looking for primes in the field of Gaussian numbers, what we're really doing is we're looking for prime ideals in the ring of Gaussian integers. To find these primes, what we actually can do is just take the usual prime numbers and see how they could possibly factor inside the Gaussian integers. So let's look at the odd primes first. We'll get to we'll get to the prime number 2 later. An odd prime can obviously either be congruent to 1 or 3 mod 4. If your prime is congruent to 1 mod 4, then it turns out we can always factor that prime number non-trivially in the ring of Gaussian integers. I've written here a couple examples of how that might work. In the example I have here, for example, the prime 4 plus I is a prime that we say lies above the prime 17. And here's a description of what exactly that means. I should mention that there are other ways one could write a factorization for such a prime, but it will always be unique up to multiplication by a unit. And by the way, in the Gaussian integers, the units are plus and minus 1 and plus and minus I. That will come up a little bit later. On the other hand, if the prime is congruent to 3 mod 4, it turns out that prime will always stay prime in the Gaussian integers. In other words, there are no new primes that lie above that prime the way 4 plus I lies above 17. When this happens, we say the prime is inert in this extension. So the only prime that we haven't considered yet now is the prime 2. In the Gaussian integers, 2 factors like this. So this one is a little bit different because we have this squared here. You can ignore the I, which, like I said earlier, multiplication by a unit in a ring, we usually ignore that, especially when we're talking about primes. So because 2 factors as the prime 1 minus I squared, we say that 2 is a ramified prime in this extension, and its ramification index is the power 2. And again, 1 minus I will be the prime that lies above 2. So these few cases we've looked at here actually covers all the different possibilities. In any number field, your rational primes can either be inert and remain prime in the field. They can split and have several primes, always finitely many, but you could have many, lying above a particular rational prime. Or it can be ramified, like 2 was in the Gaussian integers. And obviously in other number fields, it'll be a lot more complicated to compute because the Gaussian integers are kind of nice. It's particularly difficult to compute if the new ring of integers that you get isn't a unique factorization domain. That can happen. For example, all of these rings here are not unique factorization domains. So finding the prime ideals in that ring is a little bit trickier because those prime ideals don't have to be principal, and so it's harder. But the concepts and the properties of all the primes are exactly the same. It's just finding them is a little bit harder. And just like in the rational numbers, we had the description from my last video where you can take a prime and have a p-adic absolute value that you can define on the rational numbers, and then topologically complete the field to form the field of p-adic integers. Any prime in a number field, you can define a p-adic absolute value on that number field for that prime, and you can topologically complete that number field to make another field that's going to be very similar in property to any of the p-adic absolute values that come as completions of Q. One thing I haven't yet talked about here is the usual absolute value and how that might change or not in a number field. It turns out that yes, the absolute value, the usual absolute value, will also have several different absolute values lying above it in a number field. Before I get into that, a little bit of vocabulary. We tend to call all of these different absolute values, we call them places. And we say that the places that lie above the usual absolute value, those would be the ones that don't satisfy the strong triangle inequality that I mentioned in the p-adics video. We call those places the Archimedean places. And then any of the absolute values or places that do satisfy the strong triangle inequality, those are ones that always come from actual primes. We call those non-Archimedean. So then the number of Archimedean places that a number field has can be computed by looking at the embeddings of that number field into the real numbers or complex numbers. So for every different distinct embedding of the field into the real numbers, we get what we call a real place, and every embedding that you can get from the field into the complex numbers, we call that a complex place. And those complex places always comes in pairs by the complex conjugate. And that's all I got for this video. This has been your introduction to number fields and the primes or places in them. If you have any questions or want to suggest a topic for a future video, leave those in the comments below. And if you want to record a video for us, please do get in touch. Thank you for watching and thank you for learning.